Okay, so let's start. So it is my pleasure to have Edward Timko from Georgia Tech, and he will be talking about Gelfand transformations and boundary representations of complete Nevanlinna-Pick quotients. So please.
Thank you. I'd like to start by thanking the organizers for allowing me this opportunity to talk to you today. And thank you all for coming by to hear my talk. So as I said, I'm going to be talking about Gelfand transformations and boundary representations. Most of this talk is going to be phrased in terms of the Drury-Arvidsson space and quotients in that context. But at the very end, if there's any time available at that point, talk a little bit about how this applies to other spaces with similar properties. I'd also like to say that this is based on joint work with Rafael Kalatra conducted at the University of Manitoba, where I was partially supported as a Pacific Institute of Mathematical Sciences postdoctoral fellow. So I'm going to begin by giving an overview of what this talk is about, sort of this big, very broad picture. I'll get into the specifics a little bit more in the following slides. But first I want to introduce the pertinent objects. First is that I'm going to let M denote the multiplier algebra of the Drury-Arvidsson space H in D variables. These can be just finite integer. We'll let B denote a weak star closed ideal inside of the multiplier algebra. And we're going to have two algebras, AB and MB, which I'll define in detail in a little bit, where one of them, MB, you can think of as just being a quotient, and AB sitting inside of this quotient of the multiplier algebra, MB. And the one of the core questions that we want to answer that sort of a lot of these things wrap around is the following. When is the identity representation of the C star algebra generated by AB, the so-called boundary representation for AB? I'm going to tie this into a number of things, most significantly to the question about properties of the Gelfand transformation of the algebra AB. But to give you an overview of how the talk's going to go, so I'm first going to set down some preliminaries on what I mean by boundary representations. What are these algebras specifically? Then I want to briefly connect this, show how this connects with the ideas of essential normality of a certain model couple of operators and Arvidsson's notion of hyperrigidity. I will then explain this connection between boundary representations and the Gelfand transformation as it appears in the title. Then talk about what is known in the situation where D is equal to 1 and where we find ourselves back on the Hardy space of the disk. And then I'm going to go over a collection of sort of sufficient conditions to guarantee that we know that we have identity representation being a boundary representation. So first, I'm going to go over what these algebras are, A, B, and MB. So as I said, B is going to be a weak star closed ideal in the multiplier algebra of the Drury-Arvidsson space. And HB is just going to be the orthogonal complement for sort of the range of the ideal B. So co-invariant for the multiplier algebra. And one assumption that I'm going to make throughout the talk is that the dimension of this space HB is strictly greater than 1. And this is sort of a non-triviality condition, and it simplifies a lot of statements that you would otherwise you'd have to have sort of special conditions for okay, unless the space is dimension 1. So let Z1 through ZD denote the coordinate multipliers on the open unit ball in CD, by BD. And I'm going to let Z sub B denote the D tuple of operators on H sub B that you get by taking the coordinate multiplication operators and then just compressing them down to this co-invariant subspace HB. Then AB is the norm closed unital algebra generated by this D tuple, and MB is the weak star closed unital algebra generated by Z sub B. So when B is taken to be, for example, the zero ideal, A sort of is this Drury-Arvidsson version of the disk algebra, as it were, and MB just becomes the multiplier algebra in that particular case. A few remarks. One is that you can, as I said, you can think of MB as being a quotient algebra like this. where this identification is up to a complete isometric isomorphism, and I think weak star homeomorphism. And important point for what follows is that one could show that the C-star algebra generated by A sub B contains the compact operators on A sub B. So this is what the algebras that we're interested in are. So what are these boundary representations I mentioned? Well, for this, we're going to let fractor A denote a unital operator algebra, and C star of A, the C star algebra that A generates. And an irreducible unital star representation pi of C star A is a boundary representation for the algebra A. Whenever it has a so-called unique extension property, which is that the only completely contractive linear extension of pi restricted to A back up to the C star algebra is just pi itself. So you only have one choice for going back up to the C star algebra. The collection of boundary representations are important for many reasons, but one of them is that they connect with they form what's called the non-commutative Choquet boundary of Arvidsson, and this can be used in constructing the famous C star envelope of A. If you're not familiar with what that is, you can sort of think of it as the smallest C star algebra containing a completely isometric copy of A. Right. And what we want to know is when is the identity representation one of these boundary representations for this particular algebra A sub B. So right. Now we'll talk a little bit more about these ideas. And one of these things I want to connect in is, as I mentioned, Arvidsson's notion of hyperrigidity. And what does that mean? Well, an operator algebra A is hyperrigid if the C star algebra it generates, hyperrigid in the C star algebra it generates if every unital star representation of the C star algebra has this unique extension property relative to A. And this is sort of an idea first brought out by Kennedy and Shalit that we sort of isolate a particular part of and generalize is the following, is that following statements are equivalent. AB is hyperrigid in the C star algebra it generates if and only if ZB is essentially normal and the identity representation of the C star algebra generated by B is a boundary representation for A. Now, remembering correctly, in Kennedy and Shalit's paper, for the type of ideals that they're considering, this part here, the identity representation being a boundary representation automatic, and so you have this equivalence between, in that context, between hyperrigidity of A sub B and Z sub B being essentially normal. So what we were looking at is, okay, what we did was say, well, okay, well, you can apply this to this sort of broader class of ideals, but then you need this additional knowledge about when is the identity representation of boundaries. So that's what we're going to explore some more of. But now, where does the Gelfand transform of the title fit into all of this? Well, I'll let gamma denote the Gelfand transform of A for short. The first thing I want to mention is that if we have a norm-closed unital commutative operator algebra A, then the following statements are equivalent. First, that the Gelfand transformation is completely isometric. And second, that the C star envelope of A is commutative. So this is one reason why, one connection with these boundary representations, why we're interested. Another is the following, is that if A is a norm-closed unital commutative operator algebra on a Hilbert space of dimension 2 or greater, and we know that C star of A contains the compact operators, the ideal of compact operators, then if we consider the following statements, one, gamma being completely isometric, and two, the identity representation of C star A not being a boundary representation for A, then one implies two. So the Gelfand transformation being completely isometric implies that the identity representation is not a boundary representation. But if you know that C star A mod the compacts is commutative, then these two statements are equivalent. So this is sort of still in the abstract. How does this, well, how does this change when we look specifically at the algebra A sub B? Well, if you combine some of these previous ideas with some more specific properties of the essential norm, you can get the following. which is that these two statements were equivalent. The Gelfand transformation of A is completely isometric, and B, the identity representation for C star A is not a boundary representation for AB. Or as the way that we'll usually want to be looking at it in this talk is that the identity representation is a boundary representation for A precisely when the Gelfand transformation is not completely isometric. So what we'll be looking at is a lot of cases where we can know that the Gelfand transformation is not completely isometric. Quick comment though is that we'll also be looking at sort of this property for MB, but in the above theorem, you can't replace AB with MB generally, and this follows from some results of Fong and Xia from 2011 that prevents this from happening. Right. So let's get down to a little bit more specifics. When univariate setting, what ideal B is going to be of the form theta h infinity, where theta is some inner function in h infinity. And by putting together some ideas of Arvidsson and sort of repackaging it in the language that we have here, what you can say is that the Gelfand transformation matters only if you know that the spectrum of this model operator, the Z sub B, contains the unit circle. Right? So this is a complete classification of when you have complete isometry for the Gelfand transformation based on this spectral condition. And there's also a question about what happens for MB. Well, you can combine some work of Saracen from his work on interpolation with Arvidsson and some results of Moore and Nordgren to say that, well, the Gelfand transformation of MB is not completely isometric under the assumptions that we had made earlier. All right, so this is sort of, this happened, but what can we do in the full multivariate setting? And like I said, we have a bunch of sort of sufficient conditions for when we can say that the Gelfand transformation is not completely isometric. And I'm going to go through a number of these right now. And one of the first ones that we looked at is the case where A is homogeneous. Okay, so what do I mean by that? So remember that a polynomial P is homogeneous is that when you scale the argument by some value lambda, that the polynomial correspondingly scales by some power of lambda. And we say that B is homogeneous when it is generated by homogeneous polynomials. So in this context, what we can say is that if B is a homogeneous ideal, and we know that AB is not completely isometrically isomorphic to the disk algebra. So in other words, B isn't in some strong sense equivalent to the disk algebra, then the Gelfand transformation of AB is not completely isometric. And this result sort of improves on some earlier stuff, some earlier results of Clotra and Hartz, where the improvement is essentially that before there was this hypothesis about the model ZB being essentially normal, and the methods that we use here allow us to remove this condition on essential normality. Another context where we have where we can provide an answer is in the context of approximation sets. So recall that compact subset of CD is an approximation set when the restriction of the polynomials to K form a dense subset of the continuous functions on K. In the univariate setting, there's a theorem of Laurentiev that characterizes when this happens in the case that we're interested in. But in the multivariate setting, we don't even know of any complete characterization of approximation sets. But various sufficient conditions are known. One is that K be polynomial convex and have so-called 0-2 Hausdorff measure. In some sense, there's no area. Another is that K could be a polynomial convex real analytic subvariety of CD. And third it'll mention is that K be totally null for the ball algebra. So again, in some sense that it's a small set. So how does this connect with the theme of the talk? Well, I'm going to let sigma of ZB denote the joint spectrum of ZB viewed as a d-tuple of operators sitting inside of MB. Equivalently, you could take sigma to be the Taylor spectrum of ZB. So that these will give you an equivalent picture in this context. But what you can say is that if we know that the joint spectrum intersect the sphere, the unit sphere, is an approximation set, then the Gelfand transformation of A is not completely isometric. Right. So that's yet another case that we have. For this next result, I want to talk a little bit more about stuff happening on the inside of the unit ball. And this has to do with whether or not you have a point of the spectrum, or as it turns out, the zero set inside the interior of the ball that is not isolated from the rest of the zero set of the spectrum. And what this does, what we're going to do here is we're going to take some ideas, again, going back to this paper of Kennedy and Schlitt from 2015, and try to generalize them a little bit, probably through a sort of broader class of ideals, and do, it turns out, move a certain base point around a little bit. But what they do is they provide certain geometric conditions on the zero set ZB, which again I said is the spectrum intersect the ball, to ensure that the identity representation, the boundary representation. And what we can show is that if you let Q denote the quotient map, where you go from the C-star algebra to the C-star algebra among the compacts, and you make the following assumptions that D is greater than or equal to 2, lambda is in the spectrum and the open ball, but it is not an isolated point of the spectrum, and lambda and B satisfy this particular quality. Between all of these things, then we can say that neither Q nor the Gelfand transformation of AB is completely isometric. And I'll take a moment to talk about what these conditions say here. And sort of the actual one that's significant is this one. Is that, okay, we're assuming that there's a point in the spectrum in the interior of the ball that is not isolated. This part right here, what it means is, in a certain sense, that is, it's requiring that we're actually having to work with D operators, because if this fails, the idea is that, well, you could apply, I'll get to this a little bit more in a minute, conformal automorphism of the ball, and this would sort of rearrange things into a position where you could say, well, we're really dealing with D minus 1 operators, and then you could drop down to sort of a lower level and try again. So this is perhaps not quite as restrictive as I think it may seem. And sort of one key feature about the Drieger-Arvidsson space that we use when we're adapting these ideas is that the composition with conformal automorphisms of the ball on the Drieger-Arvidsson space are unitarily implemented. That's useful for allowing us to pick any point so long as it satisfies these conditions. So that's what we can say about when we have a point where we know it's not isolated. How about points where it is isolated? So in this case, we're going to again look at the spectrum, and we're going to assume that it has at least 2 points, and that the polynomially convex hull of the spectrum has an isolated point in BD. Then we can say that the Gelfand transformation of A is not isometric. So not only is it not completely isometric, it's just not isometric. And the key ingredient here is that because you have this isolated point, you can use this to construct a non-zero compact operator sitting inside of AB in this context, and from there it runs through the machinery. You can say, well, it's not isometric. And we get similar results for MB, the weak star algebra, weak star closed algebra. Except now we can eliminate this condition on polynomial convexity. So if we assume that the spectrum has an isolated point in the interior of the ball, then first we can say that the Gelfand transformation of MB is not completely isometric. And if it has more than 1 point, then the Gelfand transformation is not isometric. And again, the important point here is that, again, in the background is there's this assumption that we're dealing with a where HB has to have dimension 2 or greater. Now, what we can do is we can take some of the ideas and we combine them in this following corollary, where it says that if Z sub B, the spectrum, contains at least 2 points, D is greater than or equal to 2, and there simply exists a point lambda in the 0 set, that is to say in the spectrum intersect the ball, where we have the same equality, then the Gelfand transformation of AB is not completely isometric. And if in addition we were to know that the spectrum, if we know a particular context that the spectrum of the model is polynomially convex, then the Gelfand transformation of AB is not going to be completely isometric. And what I want to sort of point out from this is a sort of way to say, what are the areas that, well, we haven't really touched on? Well, one case where we still don't know the answer is when, so earlier, remember we said, okay, we know the answer when the polynomially convex hull of the spectrum contains an isolated point. Well, what happens when it doesn't? What can we say in that context? And another is, here I said, I need the existence of a point in the interior. Well, what happens when there are no points of the spectrum in the interior of the ball? So everything's just sitting on the sphere. We have a little bit of information in that case coming from what we know about with the approximation sets. But in general, we don't have an answer. And I think this is a particularly interesting case because classically, in the one variable case, this sort of corresponds to the case when you're dealing with these singular inner functions. And so here it was like, well, this seems to suggest that we were looking for some sort of multivariate analog of what the singular inner function is, but in the context of ideals. So I think I have a couple minutes left. And so I'm going to briefly comment on other spaces that I mentioned at the very beginning. So many of these results, though not all of them, extend to the context where we're working with maximal regular unitarily invariant complete Nevanlinna-Pick spaces in place of the Drury-Arvidsson space. Briefly, what that is these are reproducing kernel Hilbert spaces over the ball with a number of special properties on their kernel K. First is that they're unitarily invariant. And so this ends up saying that the kernel has this sort of nice power series representation in terms of the inner products with Z with W. It's regular in the sense that you have radius of convergence exactly 1. Complete Nevanlinna-Pick gives us this additional power series representation for 1 minus the reciprocal of the kernel. And maximal says that, well, these B's, the sum of these B's is as large as it can be. They sum up to 1. So many of the results carry over to this context. The one notable exception is in this case where we're looking at this equality between the point lambda and the ideal B. And for that, as I said, we were really using in a significant way the fact that we can use composition with conformal automorphisms on our space and implement them unitarily. And this sort of forces us, to working with kernels that are essentially just some sort of fractional power of the Drury-Arvidsson kernel, which we recover here when do is equal to 1. All right, so that is all I have to say. Thank you for listening. If you're interested in more about this, here's the paper that this is coming from, and here are some of the references that I've used in the talk. So again, thank you.
Thank you very much, Edward, for this talk. So is there any question or comments? Okay, so if there is no question or comments, then let's thank the speaker again.
Thank you.